Hello matriculants and welcome to This is your favorite show, Learn Extra Live with me, Abram, and of course I'm joined by Phil again to have so much fun, learn more and learn extra right here on your favorite channel 319. Phil, how are you?
I'm doing great, thanks, and you?
I'm good. It's good to see you again.
Absolutely.
On grade
I've been
12.
loving it.
You know your grade 12s love you.
Oh, well, I love them back. I love them back.
All right, and what are we doing today?
Well, today, guys, we're going to be taking a look at the Chlor-Alkali Industry, and this is a section, guys, this is a place that you can milk it for marks. Please, it's in every exam. So, let's do it.
All right, tell you about doing stuff. Let me tell you about 4 things that you need to do. 1, you need to join us on Facebook. Join our community. We have over 50,000 likes on our Facebook page. And yeah, join the club. Team mindset all the way. We help one another online. And also, if we have some questions, we post them also on our Facebook page. Second thing that you need to do is to go over via Twitter and follow us on @LearnExtra. I nearly said Twitter. I mean Mix It.
Well, guys, we're available everywhere.
On Mix It.
We are everywhere.
For your Curo, you're gonna need Mix It. Yeah, they will give you the code later on, but it is PS12. We're gonna upload the assessment later on. But another thing that you need to know is that we have some notes that are proudly sponsored by Macmillan on learnextra.co.za/live. They're just for you. And one last thing, because we are talking to matriculants, you are left with 75 days, 5 hours before your final examination. Others are starting earlier than that, like the CAT paper 1. It's before the 28th of October. So there's just no more time. Let's learn.
Well, let's do exactly that. Okay, now, this is a section I love teaching because, guys, it's guaranteed to be in your paper. And it's been in every one of the papers from the last 5 years, guys. It's got to be in there because it's one of the most important industries. And it's really easy to understand if you take a couple of things into account. Okay, so what am I talking about? I'm talking about the Chlor-Alkali Industry. Now, guys, you might recognize that there are 2 parts to this name. Obviously, chlor, and that sounds a little bit familiar, and alkali. Now, that sounds a little bit like alkaline. So what we're going to be doing is taking a look at the industry of manufacturing chlorine products and alkaline products, specifically from salt. Now, that's right, guys. Table salt that you use to put over your food, guys, we can turn this into some amazing chemicals. You might say, well, is there table salt in everything? Guys, you will not believe what the chemicals are that actually come out of normal table salt. So, guys, stay really, really close because this is fascinating chemistry. I love it to pieces. And we're going to be posting an animation for you guys to watch. And if you download it on your PC, you can actually view the animated file. We're going to post up some links. It's such a cool animation that you can actually start to see where all the ions are moving inside, the chlorine, the hydrogen, the caustic soda, all of these things are actually coming out. There's a beautiful link that I'm going to be posting throughout the show, and Abram's going to do that for me, isn't he?
Yes, of course.
Fantastic, guys. So stay glued to the Facebook page, watch us, take your notes, and get those beautiful notes from Macmillan. All right. So now let's see what's on the menu today. Now, this is one of the things that I can't believe people still don't get this right. And guys, if you don't actually take a look at this, that means that you didn't listen and you didn't actually find yourself interested in this. Now, today we're going to understand and identify. Guys, you need to be able to identify the products of the electrolysis of brine. Okay, now this is not brine like somebody called Brian. Okay, we're going to talk about brine. Now, as Abram said, guys, get onto the Curio page. Grade 12, there's even a grade 11 Curio that you guys can do. It's important for you. It's on the rates of reactions, guys. That grade 11 Curio will actually benefit you guys. And it's actually going to start to prepare you for this section. It's actually all about rates and endothermic, exothermic stuff that you guys need to know. Okay, now back to our lesson for today. Identifying the products of electrolysis. So we're going to be running some electricity through some salt. Now, please, 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 don't try this experiment at home. Don't say to your mom, now Phil told me to go and take some wires from the lamp, pull off the wires and stick them in some salt water. Please don't do that. Okay, now these guys have got big industrial processes to do this. Now, you can do this safely with your science teacher at school where he'll give you the proper electrodes and everything to do this with, but please, the electrolysis of brine, and we're going to be talking about sodium chloride specifically in terms of brine. Again, not your friend Brian. Please don't electrocute Brian. Okay, and then this is the part that people really get scared of. They see this reduction and oxidation. They go, I'm afraid of that stuff, and I really, really don't like redox. Guys, it's nothing to be afraid of. I'm going to show you, I'm going to walk you through the redox of the chlor-alkali process. There's actually only 3 reactions that can happen in a whole process that's worth almost 20 marks. So guys, the redox is not something that's too complicated. I'm going to guide you through it, and I'm going to show you what some of the questions are. All right, and then this is going to be the really interesting part is we're going to find out how does industry actually use different types of cells. Now this is where that link is going to come in handy. It's because we're going to find the different types of cells used inside the chlor-alkali industry. We're going to talk about membrane cells, diaphragm cells. We're going to talk about the Mercury-Cathode cell, and we're going to see how they're actually used out in industry to turn salt into really cool chemicals. Okay, so now let's start to take a look and let's see what happens when we electrolyze brine. Now, this is one of those questions, guys, just a little bit of a hint, a little bit later for the curio, guys. If you listen very carefully about what's happening on the slide, there's a bit of a cue for some of your curio questions. Okay, so now we start to take a look at the products. Remember that products are chemicals which come out of a process. When we electrolyze brine, well, first of all, what is brine, guys? Well, here we go. So brine, and this is very important, is concentrated. It's got to be fully concentrated. In fact, it's saturated sodium chloride. Guys, now sodium chloride, for any one of you that have been listening and watching, and you guys have been taking an interest in science, and I know you have, sodium chloride is NaCl. It's the stuff that I put on virtually everything. Okay, guys, take it easy on the salt. It does cause health problems, but it's a solid. If I take it, dissolve it in a solution, I'll make up a really nice concentrated solution. I'm going to make some brine. I can make brine at home. Okay, so now electrolysis. This is where the magic happens. One thing goes out, and it goes into my electrolysis, and out come these three amazing products. Now, guys, please, I want to impress upon you. You need to know what these products are. Please, 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 you need to know what they are and what they are useful for. So I'm going to rattle off a couple off the top of my head. Maybe we'll write down some and see what comes out. Okay, so first and foremost, there we go, chlorine. What do I use this stuff for? Now, the reason it's called the chlor-alkali process is because I make chlorine. Okay, so here's my first product. I'm actually going to make a list here. So Cl2. What on earth would I use Cl2 for? Now, Cl2, just to give you a little bit of a background, is quite a toxic gas. Guys, you don't actually want to have too much chlorine around you. But most of you have smelt the smell of chlorine before because I use it in a pool. Now, most pool chemicals very often rely on chlorine to work. So pool chemicals very often rely on chlorine to work. Now, the other place that you might have smelt chlorine in the house is the manufacture of bleach. Now, that smell of bleach that everyone thinks, oh, okay, I can smell. That smell of jik. Now, especially when I'm disinfecting something and cleaning something, I'm going to use some bleach. And that's one of the other things that I use chlorine for. It's a very good disinfectant. Right, that means that it kills off all those nasty germs. So disinfectants. Now, all of those toilet cleaner products that claim to kill all the germs inside the bowls, and you see all the germs dying, chlorine is the baddie that's gone in there and killed all of those germs. Okay, so chlorine is very good at killing viruses and bacteria and fungi. Okay, so it's a fantastic disinfectant. But guys, this should give you a little bit of a clue. If it's killing the bacteria, guys, it's not good for me either. So guys, steer clear away from all of these things. So chlorine is quite a toxic chemical. Okay, but it's very, very useful. Obviously, I want a nice blue pool. I want some nice white clothing, and I want to have sterile, all sorts of things. I want to make sure the bath is nice and clean. There's not too many germs, and there's no germs inside the toilet. Okay, so here we go. Next on our menu of delicious products, here we go. Hydrogen. Hydrogen is some pretty useful stuff, guys. You might say, okay, well, where on earth have I used hydrogen before? But if you're thinking that, that means that you haven't remembered some of your chemistry from earlier on in the year. Now, what do I do with hydrogen and double bonds? This is something I might have heard of before. Guys, right, you're going to see what's happening over here. Margarine, guys. Margarine is a product of hydrogen. Hydrogen comes out as soon as you bubble hydrogen through sunflower oil at very high temperatures and pressures. What you're going to find is that it actually changes into a more saturated fat. So this is a little bit of organic. It changes into margarine. Once it's cooled down and filtered, it's sold to you as margarine. Okay, so that's hydrogenated fats. Now, what else do I use hydrogen for? Now, there's many different things that I can use hydrogen for. So I want you to start thinking about these. Now, these are some possible future uses for them. Okay, fuel cells. Okay, now fuel cells are a very special type of battery that can use hydrogen and oxygen from the air to create electricity. Really nice thing about this is if I have a car which uses hydrogen, all that comes out of the exhaust is water. And that's really amazing. So hopefully we're going to move on to a hydrogen economy fairly soon, and we're not going to be burning oil products. We're going to be burning hydrogen instead. All that comes out is nice, clean water. The problem is we've still got to produce the electricity. So I want you to give that a little bit of a thought, because you guys are our future engineers. Okay, so margarine and fuel cells. And what else? Guys, I don't know if you've ever heard of a little thing called a satellite. Some of you are watching us right now with the use of a satellite. And without some hydrogen as rocket fuel. It was a rocket that took that satellite out into space. Now, hydrogen is some pretty good stuff when it comes to rocket fuel. Hydrogen is very explosive. It explodes really nicely and sends those rockets up into space. And rocket fuel is one of the great uses for hydrogen. Okay, now there's another product out of this chlor-alkali process, and it's where the second part of the name comes from. Over here, sodium hydroxide is the last of our products. So sodium hydroxide has got a couple of other confusing names. I just want to give them to you as the show goes on here. Sodium hydroxide has got a formula. I'm hoping that you managed to guess it. Right, NaOH. Guys, it's got some other names as well. Sodium hydroxide is also sometimes called caustic soda. Now that's its old name. So caustic soda. Right, and it's sometimes also sold under the brand name of lye. Okay, so these are two other ways. Now, this is not like lie, like you lie to your parents. I hope you don't. Okay, caustic soda and lye. Now, this is another dangerous chemical, guys. You shouldn't ever touch this stuff with your hands, and I'll tell you now why. Because caustic soda, when it meets biological materials like fats, like the fats inside your skin, it makes soap. Right, now, this is one of the biggest uses for sodium hydroxide, is to make soaps. Okay, now that reason that some alkali solutions actually make a soapy feeling on your hands, and this might gross you out a little bit, is it's actually turning the dead skin on the surface of my hand into soap, guys. You're busy washing your hands with human soap, and it's a little bit gross. Okay, so guys, sodium hydroxide, please keep it off your hands. It actually eats off the outside layer. It's very, very dangerous stuff. Okay, so it is used to manufacture soap, and you don't have to eat off the surface of your hand to clean it off. Now, normal plant fats are a really nice source to make soap from. And here, of course, is the other big use for sodium hydroxide. Sodium hydroxide is very good at dissolving fats. Now, when I chop down a tree like the ones which are grown out in Mpumalanga and in KZN specifically for paper, those trees are grown for paper. When I chop that tree down and I want to make paper out of it, what I have to do is dissolve out the lignin. Lignin is a fat that binds together the cellulose, for you life science fundies out there. So now, soap and paper production. So paper production is one of the major uses of sodium hydroxide. So paper production, what they do is it dissolves out the lignin between all the cell fibers. Okay, so there we go. It's paper production is one of the major uses of sodium hydroxide. Very handy stuff, this. I want to make sure that I can supply my industry with all three of these. So let's just recap before we go for a quick break. Chlorine is really good at cleaning stuff. Guys, you smelt it in pool chemicals, in bleach, in disinfectants, especially in those ones that you use to clean the toilet or surfaces that you really want to keep clean. And then hydrogen. Hydrogen is my favorite because I believe that hydrogen is the fuel of the future. It's used to manufacture margarine. It's potentially useful in fuel cells, which is a special type of battery. And then as rocket fuel. I'm a big fan of rockets because obviously the rockets carried up the satellite, and that's the reason that some of you can actually see me, because the TV signal is bouncing off that satellite. And then lastly but not leastly is my caustic soda or my sodium hydroxide. Guys, you've got to know these alternate names because sometimes it says caustic soda was added or lye was added. These are industrial names for sodium hydroxide. Okay, so NaOH is used to manufacture some soap, some paper products, and obviously this is one of the other things that actually confuses people, is that sodium hydroxide, whoops, I'm scrolling all the way down there. Let's make sure I don't lose my sodium hydroxide. I worked so hard to get it. All right, there we go. Sodium hydroxide is also used in the manufacture of bleach as well, because bleach is made up of sodium hydroxide and chlorine together. Guys, two very dangerous chemicals. That's why your mom says stay away from the bleach, guys. Okay, well, what I'm going to do is I'm going to give you guys a little bit of a break, because I'm sort of running away from things here, but I want to give you guys a little bit of a chance to share stuff on the page, get on the Curio, Abram, what do you think?
I think so too, but I have a quick question for you.
Great.
They say that margarine is one molecule closer to being a plastic.
Okay. All right. Now, there seems to be a bit of an urban legend or a myth about margarine being artificial. Okay, now guys, that is partly true, but it's nowhere near being a plastic. Okay, now margarine itself is natural oil which has been changed slightly to make it slightly more solid. If you want to go back and look at your organic chemistry, I've taken an unsaturated plant fat and I've raised its boiling point and its melting point so that it actually becomes a solid at room temperature. I've just added in a little bit of hydrogen. Guys, you haven't actually made plastic, you're not eating plastic. I would recommend not eating too much margarine because your body doesn't actually recognize the stuff too well. So guys, margarine does stick to your body a little bit more than butter does, but don't take health advice from me. I'm not your dietitian. But guys, it's not plastic. Don't panic. Your mom's not putting plastic on your sandwiches.
I like that. Well, I like the part that you're not just a dietitian. You're not a dietitian.
Yeah, absolutely.
Well, Mansito, stay tuned because after the break, we'll continue more on what you need to know and what you have to know for your exam as a matriculant. See you after the break. Welcome back, Mindsetters. Now, I hope I have some good news for you also. If you'd like to learn more with us, on Saturday, we're having a Saturday live show just for you. So I'll be giving you more details on the times of which you can tune in for Physical Sciences Grade 12. We'll be revising, we'll be helping you on our Saturday live show. So Phil, let's continue.
Let's do it. Okay, guys, before we went away from the break, I told you that you could make chlorine, hydrogen, and sodium hydroxide using the electrolysis of brine. Now, remember that brine was not a person. Brine is concentrated sodium sorry, I'm getting completely confused here. I'm getting carried away. So brine is concentrated sodium chloride, just like table salt. Now, what happens when we start to electrolyze this? Let's actually take a little bit of a closer look. You'll actually notice when you run electricity through brine, you'll actually notice that there's two gases manufactured over here. So I've got a negative electrode over here and a positive electrode taking place over here. Now here's my solution. So let's actually just draw in my solution here. So my solution is taking place on the inside there, and guys, this picture is already inside the notes. Go and get them. They are sponsored. They're there for you. Right. Now what I notice is that the negative electrode, what I'm going to find is that hydrogen gas, H2, is the result of electrolysis of brine. Now this is a bit surprising because in the past you've said electrolysis splits two elements of one substance. But which substance did I give you? I gave you sodium chloride. Oh, that's very confusing. I've got aqueous sodium chloride. Where does the hydrogen come from, guys? I want to leave you to challenge that. Start posting up your ideas on Facebook. I want to know, where does the hydrogen come from if I only gave you sodium chloride? There's a bit of a trick to this. But before I give you the answer there, I want you to think, I want you to rack your brain. Where does the hydrogen come from? Now let's take a look elsewhere inside the cell. Now if I start to take a look at the other electrode, I've got these really nice yellow bubbles, these bright yellow bubbles. Those are bubbles of chlorine. Guys, chlorine is a yellowish greenish gas and it's produced at the positive electrode. So there we go. Chlorine gas is my other product. So Cl2 is my second product. Along with H2, I've got two gases which come out. Now the third product, the sodium hydroxide, which forms the NaOH, you're not going to see that stuff. Guys, it's dissolved inside the solution. It's still there. All that needs to happen is I need to separate it out and sell it. But now, here's the problem, guys. This is the reason that industry does not do this in this particular way. Guys, if you mix hydrogen gas and chlorine gas together, they actually form a very dangerous mixture. Now, hydrogen and chlorine as a mixture will even be set off by sunlight. They'll actually explode if they're exposed to sunlight. So guys, never, never, never mix hydrogen and chlorine together. Not only is chlorine very toxic, it used to be used as a poisonous gas in World War I, chlorine is unbelievably toxic. So if you're smelling lots of it, guys, that's dangerous. So hydrogen and chlorine need to be separated unless I want this to blow up like a bomb. So now industry has had to think very long and hard about how they're going to separate the hydrogen and the chlorine. And they spend a lot of money on doing this because obviously it's a safety issue. Now, I asked you a little while ago where the hydrogen comes from. Has anyone answered that on the Facebook page? Are people starting to guess where does the hydrogen come from?
Not yet.
Okay, guys, you're a little bit slow. I'm going to give you a little bit longer. Now, I want to start talking about my hydrogen, my chlorine, my sodium hydroxide, but I need to know where all of these chemicals come from. So, sodium hydroxide, that makes sense. I put in some sodium, that makes sense. I put in some chloride, that makes sense. But now there's two parts to this puzzle which don't make a lot of sense. And here they are. Where does H2 and where does OH come from? Now guys, the last time I took two H's and one O, what does that make? This means H2O, guys, and there's your answer. H2O is where some of the other reactions are taking place. You'll notice that instead of the sodium reacting, sodium is a spectator ion. That means that it does not participate. So guys, if you remember from redox chemistry, ions which do not react are spectator ions. Now, long before we get into the redox, what I want to show you is some really cool stuff. We're going to start
Can I ask you a
seeing.
quick question before you move from that?
Absolutely, let's do that.
You spoke about the dangers of chlorine.
Yes.
Can it be used to unblock drains?
Okay, now very good question. Okay, now chlorine itself is not used to unblock drains. Sodium hydroxide is. Now, if you go to the hardware, you can actually buy these white pellets, and those are sodium hydroxide pellets, and those pellets are sodium hydroxide drain cleaner. Now guys, you've got to be very careful with sodium hydroxide. It's so crazy that it actually eats glass, guys. It eats the porcelain off the inside of the toilet. It eats everything. Your fingers, everything. So guys, please stay away from it. So if you are using it, get your dad to help you, get the plumber to help you. It does open up drains. But chlorine itself is not used to open up drains. So that's a really nice question. I've got to make sure that I'm using the correct thing for the correct use. Okay, so now we've decided that there's several things which can react inside here. Let's start to take a closer look and see why these reactions actually take place. Okay, so now we've decided what our products are, but now the question is, I need to start off first of all with what I've got. And that is sodium chloride. Guys, mountains and mountains and mountains of ultra pure salt. These companies go to extraordinary lengths to make sure that the sodium chloride is very, very pure, because you don't want any other products. If you put impure stuff in, you're going to get impure chlorine and hydrogen and sodium hydroxide out, and that's going to make a mess. Now I've got to clean up three things. So the sodium chloride which goes in is way, way, way cleaner than the stuff you put on your food. In fact, it would probably be more healthy. Okay, so sodium chloride solid. I dissolve this in H2O. And what comes out? Now here's where the magic starts to happen. I've got a sodium plus ion and a chloride ion, and those can react. Those are potential reactants. Now guys, I'm going to put something on the screen. I want you to take a deep breath. We're going to love redox today. What's going to happen is I'm going to show you how to do the redox. Now I've just picked out the reactions which are important to us. Now if you've got a redox table, or if you've got the notes which are on the website in front of you, you'll see exactly the same thing. These are just tiny portions. I've taken some from the top and I've taken some from the bottom. These are directly on your redox table. Okay, now my first job, I'm going to run you through how to do redox again. My first job, always when I get a redox table, is to circle or to find out the species that I have. Now you might say, okay, well this is not life sciences. What are you talking about, species? Guys, species can describe any chemical reactants. It can be an ion, it can be an atom. When I talk about a species, I say that sodium plus is a species, just like animals running around in the game park. So here we go. So sodium plus is a species. I know I have that because I put in sodium chloride. I know that I've got chlorine as a minus. Now you might notice, I'm not circling the whole reaction. Guys, please don't get into the habit of circling entire reactions, because that's actually going to make redox way more difficult. Circle only that tiny little chemical that you got. Now, the other trick is to circle the other things which you have. All right, I know that I made a solution. That means there's plenty of water around. So there we go. Water is also a reactant. Now, what you'll notice is that water is competing against these other two reactants. Now something very special happens inside an electrolysis cell. What you'll notice is that I usually do pick the best reactant. So on the left here, so increasing oxidizing ability, I want the best. Now what will happen is I can, yes, say, okay, well, my water is the best reactant. Now there is a type of cell where the sodium actually reacts first. Now I want you to think, why would sodium react rather than water? Now think about what we're trying to do. We're trying to run electricity through a salt solution. If I have electricity, and I'm going to show you the diagram again to give you a bit of a clue. If I have electricity running through the solution, I've got two charged metal rods sticking into the solution. Those rods are very attractive as far as this goes. Now those rods are highly attractive when it comes to ions. So very often you'll find that the ion is better at reacting. Now in this case, so what happens if I do react some sodium ions? What you'll notice is that I get a spontaneous reaction between sodium and water. So that won't last very long. So guys, I'm going to ask you to take it on faith for the moment, and I'll come back and explain it at the moment, is that water is the reactant. Now, at the other electrode, I'm going to ask you to take this on faith again, and I'll explain it in a moment, is that between these two, that chloride ions are actually a better reactant, even though they're lower down on the table. Why do you think chlorine is preferred to water? They're right next to each other on the table, and it looks like water is actually better. Why chlorine and not water? The arrow tells me that the best one is found on top. Why don't I choose water? Now guys, the reality is that sometimes water does react. But this is why I use very concentrated sodium chloride. That means that there's a very large amount of negative ions around the positive electrode. In fact, they're completely coated, and hardly any water is going to be touching that electrode at all. So I want to make sure that my chloride ions stay at a very, very high concentration, so that chloride ions and water are my reactants. Now you might say, okay, Phil, I don't have time to reason through all of the stuff in your exams, and you're absolutely right. Guys, you are pressured in your exam. So how do I know which reaction to choose? Well, here's your clue. Guys, look at your products. Take a look. The product of reacting Cl- is one of the products I'm after. I'm going to circle them in green. Absolutely. There we go. Chlorine is one of the products that I'm after. So guys, this is the reaction that I'm in the business for. Water reacts to give me H2, there's the giveaway, and hydroxide. That's what I want, guys. I want hydroxide, I want hydrogen, I want chlorine, and this is the way that you identify which reactions to use off my redox table. Now, electrolysis can be a bit of a tricky place, so what I'm going to do before we take a break is I'm going to write down the reactions which most commonly occur. So let's practice taking them off the redox table. So you always start from the side of your reactant which you chose, and in this case, I chose water. And then I read it out off my table from that side. Now, it's quite easy for the top one. So what happened to water? I took two water molecules, and what happened to them? They changed slightly. I added electrons to them. And then what happened is they changed into hydrogen and hydroxide ions. Now, guys, you can get this directly off your table, so there's no need to copy this incorrectly. The only thing to remember is that you don't have a bidirectional arrow anymore. When you write this out as your reaction at your anode or your cathode, single direction arrow. Let's go for the next one. What did I choose? I chose chlorine. There it is. I've colored it 3 different colors here. Chloride ions are my reactants. So there we go. So 2 chloride ions react by giving away their electrons, and I'm giving you a bit of a clue as to what I'm about to talk about. Chloride ions give away their electrons and leave behind that chlorine, which I can use to clean my pool, make jik, clean toilets, bleach paper, all sorts of things. Now, these are the 2 reactions which are the most important. Even if your redox is not that great, guys, these reactions are everywhere. They are ubiquitous. They are in every single section. You will always find that my products of, let's just circle them to make a point here, hydrogen, hydroxide ions, and chlorine gas are all products of this. Now, what happens after this? What happened to the sodium hydroxide? Where did it go? What did it do? Now, taking a look over here, I notice that there's a negative ion that's looking a little bit lonely. So if I take a closer look, that looks like a perfect match for some sodium ions. So what you'll notice is that sodium ions and hydroxide ions are where my sodium hydroxide actually comes from. Sodium ions did not participate in most of these reactions. Now, what I'm actually going to do is I'm going to give you a little bit of a link. Is the link up for the animations yet? We're going to post it?
We're going to post it right now.
Excellent. And we're going to post this animation. Guys, I actually want you to go and follow this animation. It's mind-boggling that people actually made such a cool animation. But guys, I think something is lost on TV. You need to see this on a computer screen in front of you. Big, steal. No, don't steal, guys. Okay? Right, it's just an expression, but what I want you to do, get yourself in front of a computer and then actually take a look at this animation. It's absolutely important that you actually do this. Now, what I'm going to start doing is I'm going to start taking a look at animations about the chlor-alkali industry. What I've got behind me is a link to a page, a company that does the chlor-alkali process. These guys have got these 3 different types of cells animated beautifully on their table. They actually show you how each one of them works. I'm just going to run you through some of them quickly. So if you want to know about the diaphragm cell, not a problem. We're going to look at it after this break. Even cooler, this is what they do. They say, view the animated diaphragm cell process, and what they actually do is they show you the animation in the process. Now, I'm going to let that digest for a little bit. I'm going to ask you guys to surf on over to that link. I think it's time for a short ad break so that they can catch up. You can post the link, and then we can sort this all out.
Yes, we're about to do that, but I just want to say this shout out to all the mindsetters that are on the page and getting the answers right, such as Shikash, PWM, Sovo, Reflector, always on the page. Thank you very much, guys. Gentle, I can see all of you guys, Emmanuel and Maureen, enjoying the show. Keep loving the show and enjoy it, because we'll see you after the break. Welcome back, Matrix. Now, 2 reminders. 1, you can take the Curio assessment via your Mixit or via curio.co.za. Your code is PS12. Get to that Curio assessment and fill in the answers. Make sure that you don't skip any question. That's just how you should do it, so that we can understand that you understand. That's how we roll. And the second reminder is that we are in need of someone. We need to hire someone who is interested in doing our grade 10 to grade 12 CAPS content development, review, and video presentation. So if you know of that person, tell them to go to mindset.co.za/land/jobs, and the closing date is the 26th of August. For now, back to you, Phil.
Thanks so much. Okay, well, it's great, guys. You get to work with us, so please apply out those jobs. Okay, but now we're back into electrolysis. Let's get you through matric first. Here we go. Now we're going to start taking a look at the first type of cell, which is actually used in industry. Guys, this is called a diaphragm cell. Now, guys, this link that I've got over here is absolutely incredible. Please surf on over there. We've posted it up to the Facebook page. It's amazing. It gives you a really nice run through on how chlorine is produced, how the diaphragm cell works. Actually tell your teacher about it, tell everyone about it. This is one of the ways that chlorine is actually produced. Okay, now remember I told you the hydrogen and the chlorine cannot touch each other. All right, so the first thing that I start to use is a diaphragm. Now, what the diaphragm actually is this porous material. But now the problem is, in the past, they've used asbestos. Now, asbestos is really, really horrible stuff, guys. Asbestos makes this horrible powder which gets into your lungs and stays there for the rest of your life. Now, this is one of the reasons asbestos is not used in roofing and brake pads anymore. Asbestos is really, really nasty stuff. Now, this type of cell, for this very reason, is being phased out. Guys, you're not allowed to build any one of these in most nations anymore. Diaphragm is built out of asbestos, not really cool. But let's start taking a look at the chemistry. The chemistry is really good. The chemistry starts off with our friend brine. And remember that brine was sodium chloride, which is aqueous, nice and concentrated, into this compartment over here. I've got a positive electrode. Now, think of yourself as some brine. I'm brine, I've got a positive piece, I've got a negative piece. I find a positive electrode, what might be attractive? What you'll find is that at the positive electrode, the negative chlorine reacts. Negative chlorine coats itself all over that positive electrode, and this is where it's changed into chlorine and it leaves as a gas. Guys, this is oxidation taking place. This is the anode. Okay, so there we go. Guys, the anode over here is where chlorine is manufactured. Now you might ask yourself, okay, well, why are these two blue lines at different levels? Well, what I've drawn in is a blue line at a very high level. That is my brine solution. Now the brine solution slowly makes its way into the second compartment over here. It carries with it some sodium plus ions. It's still got some chloride ions, and it's got lots of water, and that's what's going to react in the second compartment. Over here, this negative electrode is going to react with water. So H2O, our good old friend water, is going to react and change into hydrogen gas in that compartment. That process, if you are watching very carefully before the break, is reduction. Reduction makes this the cathode. So our cathode over here is the place where I get hydrogen out, and my sodium hydroxide is one of the products that comes out of here. But now here's the problem, guys. My caustic soda or sodium hydroxide, which comes out, is not pure. Okay, in addition to asbestos being this horrible, nasty chemical that gets inside my lungs, the sodium hydroxide has still got some Cl minus, and guys, that's bad. It's really difficult to separate ionic solids because they all behave in a kind of similar way. So Cl minus is one of the impurities or contaminants of my caustic soda. Guys, that caustic soda is not clean, and generally it's the stuff that you would use to clean drains. Okay, they don't need very high grade caustic soda to do that. Okay, so guys, the diaphragm cell was one of the first ways that they managed to figure this out. But the chemicals were not that pure. The hydrogen and the chlorine were kept separate, and that's absolutely great. But it didn't solve all of the issues. Okay, now this next type of cell has got some obvious advantages and disadvantages. Now, guys, this is electrolysis inside a Mercury-Cathode cell. It's called a Chlor-Alkali cell. Now, before I take a look at this, I actually want to run you through one of those animations. Now, inside this animation, I've got the diaphragm cell actually taking place, and you can actually start to follow some of the chemicals that go in here. On the top left, I can see some brine, the saturated brine, sodium hydroxide, and sodium chloride, and water which is entering over there. And what actually starts to happen is the Cl minus is very attracted to the positive electrode and changes into chlorine. So I'm actually going to draw all over here. So let's do exactly that. I'm going to start highlighting bits and pieces, and let's do exactly that. So what I'm going to find is that sodium chloride is going to be entering on this side on my diagram. What happens is that my chlorine over here, my Cl minus, is going onto that electrode, and I notice, and I want you to look at this piece of the screen. I see that there's all sorts of ions which make their way through there. I want you to take a look. Some chloride and some sodium ions come through. Sodium is fine. I need it for the sodium hydroxide. But the chlorine, take a look at that. The chlorine is coming through as well, and that's a bad thing, guys. I don't want the chlorine inside my cathode compartment. Okay, so my diaphragm cell sorts out some problems, but leaves others. So what I'm going to do is I'm going to take a look at other types of cells. Now, here came the next step in the evolution of the cells. Now, this one looks very complicated, and in some ways it is. Once again, we start off with our brine, which is sodium chloride, which is nice and aqueous. Okay, it comes into here, but now here's the really weird part. The cathode is not made of another metal. The cathode is actually made up of mercury. Mercury is a liquid metal. That means that it's conductive, and it's negatively charged in this cell. So I've got this big negative mercury pool sitting down at the bottom of this casing. Now, the same thing happens at the positive electrode. I change my Cl minus into chlorine gas. That's no problem. That's the same in every single cell. I take Cl minus, positive electrode, becomes chlorine. Now, what's different is what happens in the mercury. Something different starts to happen inside this mercury, and I'm going to point it out. We allow sodium to actually become a metal. Now, this is very, very strange. It's not what I told you right in the beginning. I actually get the reduction of sodium, and this is why it's called a Mercury-Cathode, because we're reducing things there. It actually changes into sodium metal. The only reason that it's allowed to do that is because it combines with the mercury, and the mixture of the two, HGNA, is called an amalgam. Now, I'm sure that you've heard different versions of this word before. I'm sure that you've heard of something amalgamated. That usually talks about companies which have come together. Now, when I've got an alloy made out of mercury, it's called an amalgam. An amalgam of sodium leaves on the side. Now, what starts to happen is I still want my sodium hydroxide, I still want my hydrogen, but here's the magic. The mercury amalgam is actually carried away and reacted separately with some water. So water comes in here and reacts with my mercury amalgam, and there we go. We've got our hydrogen coming off here. The caustic soda that comes off this process is some of the cleanest in the industry, but here's the problem, guys. The mercury which is used inside this process. Mercury is some terrible stuff. It makes its way into water systems, it accumulates in fish, and what you'll notice is that it gets more and more concentrated up food chains, and guys, that's really a bad thing. Mercury is some nasty, nasty stuff. If you see any of your friends playing around with it inside their hands from a broken thermometer, guys, tell them to put it safely inside a bottle and close it and call a science teacher. Guys, that stuff is dangerous. The reason that I say it's so dangerous is because it's a liquid, it evaporates, and this is the problem with the process. I've got hot mercury. It evaporates, and the vapors actually find their way into my body. I can't even see the vapors, and they stay there, guys. This is called an accumulative toxin. It actually finds its way into your brain and makes you crazy. Guys, and I mean horrible crazy. Guys, this is a horrible toxin, so mercury is not good stuff. So you can see why countries are starting to phase out the mercury processes. So the Mercury-Cathode makes really nice pure chlorine and hydrogen, and it makes really nice caustic soda, but here's the problem. The mercury that it produces is a neurotoxin. It's really toxic for my brain and the nerves inside my body. So guys, mercury is an obvious letdown. And there's another problem to this process. This process consumes a lot more electricity because of the two reactions. So guys, when you're starting to summarize a section, start to draw up advantages and disadvantages of these two. What I want to do is quickly run through the Eurochlor site, and let's actually take a look at the mercury cell process, and you actually get a chance to see what's going on there. So let's just make sure that we've got the mercury cell. There we go. And I can actually see the mercury cell going on there. So what I'm actually going to do, there we go. So let's just get rid of that. Aha. So now you can actually see the Mercury-Cathode cell in action. You've got the brine coming in on the top left. I want you to notice where the chlorine is formed, and the separate digester, it's called, is where mercury actually changes back into the metal and is recycled. The mercury is recycled in this, but, guys, you've got to take apart this plant someday, and that mercury has to go somewhere. I advise you to go surf on over to the site. If you've got some speakers, it really sounds cool. You can actually hear the bubbles popping. It's really cool. You can see there's gas bubbles all popping all over the place. Unfortunately, I can't transmit that over air, but I want you guys to find out for yourself. I want you to see where the ions go, where does the chlorine go, and how does the chlorine gas form. And then this mercury amalgam, the HGNA, where does it react and how does it react? Now, just a bit of a challenge for you guys. If you want to do a little bit of a challenge, how does sodium react with water? Use your redox table and you can see where your products come from again. But now, again, I said that this is not the ideal process. I don't solve all of my problems. I don't solve my energy problems. I don't solve my toxicity problems, my environmental problems by doing this reaction. So now, what am I left with? And here's where the star of the show actually comes in. I start with a membrane cell. And guys, I've noticed something. The membrane cell is inside every single exam for the last 5 years. The supplementary March exam, the November exam. The membrane cell is becoming the most commonly used cell in industry. And I'm going to run through it quickly. But basically, here's the concept. Is that brine still comes in. I still make chlorine. The same reaction happens. But what happens is there's a membrane between here which doesn't let through negative ions. It's this really amazing plastic, which is called a cation exchange membrane. Now that sounds really fancy and technical. Guys, you don't have to remember it. All basically it's saying is that I only allow sodium ions through. And that's the magic behind this. I don't let any chloride through. There's no asbestos. There's no mercury. And I get my beautiful hydrogen out this side and nice clean caustic soda. but there's always a disadvantage. Guys, this membrane over here is a trade secret. Companies do not share what they make their membrane out of because it's hugely expensive to start this process. So guys, advantages, disadvantages, I want you guys to decide. This by far is the most healthy, most economical way to go long term. There's no toxic byproducts, it uses less electricity, it makes the purest product. This is definitely the best out of all three. The reason I showed you those other two is because it introduced the chemistry and it shows you where we've been and where we're coming from and now where we're going to. Now we've got a little bit of time to jump into some questions over here.
But now quickly, Phil, what is the difference between the diaphragm cell
and the membrane?
Yes.
Okay, really nice question. Okay, so they look kind of the same, and that's the really difficult thing. Now what you'll notice is that the diaphragm cell has got a separator in the middle, but now here's the big difference. The diaphragm cell lets through everything. Okay, it lets through the sodium ions, it lets through water, it lets through chloride ions, it lets everything through, and it's made of asbestos. Now this one, the membrane cell, only lets through the sodium plus ions. And I think I've got a little bit of time. I wanted to show you what's going on with the membrane cell process over here. There we go. If you animate this, what you'll actually notice is that only sodium goes through that middle wall. So we've got the sodium ions which pass through. We get very beautiful, pure products. There is no chloride ion which can pass through that. Really nice question. Guys, go study these. I want you to be dreaming about these animations because they explain the redox and you can see where all the chemicals go. Really nice to do. How was that?
Good one.
Okay, I think we've got time for a quick exam question. So now this one came from the 2011 final paper. I wanted to talk to you about the simplified diagram. Remember what I said? The diaphragm or the membrane cell. Now this one's a membrane cell, so they swap between the two. Very seldom do they ask the mercury cell, but you have to learn it, guys. The way that I can tell that this is a membrane cell is because I've got two inputs and outputs. You can actually see that water's going in and coming out. Brine's going in and used salt solutions coming out of both sides. That's one of the indicators. Okay, now it says to write down the function of the membrane in the cell. Really nice question. What it does is it lets, now this is a really cool thing, is that it lets only the sodium ions through. So it lets the sodium ions through to the cathode. And that's the point behind using a membrane cell. It's very, very clever stuff. It's this high-tech plastic stuff that recognizes positive ions and lets it through. It rejects water. It rejects the chloride ions. Okay, now we've got a little bit of time. Let's make sure that we make it all the way through it. So it says which electrode, X or Y, so we've got to look at the diagram, and they're going to do this to you as well, is connected to the positive terminal of the power supply. Briefly explain how you arrived at your answer. So we are trying to decide if X or Y are going to be positive or negative. Okay, now it's not immediately obvious because they don't tell us what gas A and gas B is. But now here's the thing that does give it away. Water went in on the left-hand side, but came out as a compound C. Wait a minute, that sounds like a product was made. Now, here's my other clue. Brine is entering on the right-hand side. Wait a minute, brine enters on the side where chlorine is produced. Chlorine likes to go for the positive electrode. Now, on the other side, my cathode, the negative one, is where hydrogen is manufactured. Now, the way that I can talk about this is I know that compound C is most likely going to be sodium hydroxide. Sodium hydroxide is manufactured inside the cathode, and that is negative in this case. On this side, brine enters the side, and the brine always, now this is the hint, brine always enters the anode. So here we go. Brine is entering the anode over here, where negative chlorine ions would find their way onto a positive electrode. And that's how we answer that question. We're almost all the way through.
I have a question for you.
You've got some questions?
Yes.
Is it about this?
Yes.
Fantastic, let's do that.
Here's one from Sia. I'd like to know, since the membrane allows positive ions to go through it,
Yes.
why doesn't the hydrogen ions go through since they are also positive?
Okay, very good question. Okay, now what actually starts to happen inside that situation over there? Okay, Now you'll notice that the hydrogen ions are actually kept to a very, very low minimum concentration because hydrogen ions can pass through that membrane. Now, how do you suppose we actually manage to keep them down to a minimum? You actually keep the situation inside that entire cell to be very alkaline. Now, when you're alkaline, there's very few H+ ions which can travel through there. Now, even if they do make their way through there, they are still only going to make hydrogen. Even if they do make their way through there, they won't make problems. So it's not really a problem if hydrogen plus comes through, because what will happen is that hydrogen plus will get cancelled out by sodium hydroxide, and you'll actually make water again. So hydrogen ions are not a problem. In fact, that's how they make the membrane. They make lots of hydrogen ions on a plastic.
All right.
Excellent question. Is there anything else before we move on?
Can I give you another one from Letuk Tula Mhlongo? Explain why hydrogen is formed at one of the electrodes and not sodium.
Oh, okay. Very, very nice question. That needs me to go back to the redox table, but actually I'm going to draw this out for you. Now, when you're taking a look at your redox table, there's two things which compete with each other. So in the diaphragm and the membrane cell, what you'll find is that you're looking at the best reagents. Now, at the moment, I've got sodium plus, which is competing, and look a little bit further down the table, you'll see water, which is competing over there. Now, water is a better oxidizing agent than sodium. Now, that's the first and the shortest answer. But now, this doesn't really answer how the Mercury-Cathode cell works. In the Mercury-Cathode cell, you do actually get the formation of sodium ions. Sorry, sodium metal rather. Now, I want you to take a look at this. Guys, if you do manage to create sodium as a metal, take a look here. There's lots of water around. That means that sodium can react and change back into ions and allow the water to react. Doesn't matter, you're never going to be able to make sodium in the presence of water. The two will react. So I hope that answers that question. Really, really nice.
All right, a last one now from Kuku Mata. Myth or truth? Is it true that white bread is bleached in order for it to receive its white color?
Okay, absolutely not. It just means that the wheat has been washed. Okay, the husks of the wheat have been washed off. Guys, it hasn't been bleached. Don't worry, the bread is not bleached. Okay.
All right.
I think that's all we have time for.
I also think so. And Mindsetters will see you guys on Saturday from 9 o'clock. We'll be having our Saturday school. So make sure that you join us on that Saturday. But otherwise, Phil, so that now that the Mindsetters are preparing for their prelims, what would you say are the best advice in treating physical sciences?
Well, guys, you've got to draw up. First of all, you've got to have a plan, right? Failing to plan is planning to fail.
Exactly.
Okay, now the thing is you've got to have your plan, and guys, please don't just get in there and start making summaries and notes and notes and notes and notes. Guys, we've got notes. My advice to you at this stage, past paper practice, guys. You've got to expose yourself to lots of questions, and that is my best advice.
Well, that's all we have for. Remember, winners are never quitters, and neither quitters are winners. So that's all we have for you today. We'll see you guys on Saturday. We just want to say peace and thanks to Macmillan, our proud sponsor.